Welcome back. This week, moving on to Chapter 3, the bioenergetics of exercise and training. So a lot of this stuff you've heard from me before. So we covered it when we talked about muscle, some of this stuff. We covered it in 202 when we talked about metabolism. And then you've also heard it at least once from Dr. Kephart, possibly twice from Dr. Kephart. So a lot of this stuff should very much be reviewed when we talk about the different energy systems. And in fact, we even talked about it in 345, the program design class. So a lot of this stuff should sound pretty familiar. All right, so then without further ado, and again, this is something we covered in 345. So exercises or events or sports of different intensities rely on different sources of energy to fuel muscle contraction. So sports or events that are very high intensity and brief in nature. So think about things like a 60-meter dash, a 100-meter dash, right? So those are things that are 12 seconds or less, 10 seconds or less. An all-out snatch in terms of the Olympic weight lifts, an all-out clean and jerk, max deadlift, max squat, those kinds of things, right? So they're very brief in duration, high power or high intensity, but for a short time. So those types of activities then rely on the anaerobic energy system, so without oxygen. And so those rely then on the ATP phosphocreatine system. When we stretch it out a little bit longer, so events longer than 12 seconds and really longer than 10 seconds, up to 2 minutes. Now we're into the glycolytic system where we're using glucose, carbohydrates, anaerobically to generate ATP. And then if we go longer than that, we're going to start to rely primarily on the aerobic energy system. So we may still be breaking down glucose, but as we decrease the intensity, we're also going to start to work in fat as one of our fuel sources or substrates. So that's a term you're going to see a lot on this slideshow is substrates. And so substrates just means something that we break down to use for fuel. So that can be ATP, that's a substrate that fuels muscle contraction directly, but substrates also include things like phosphocreatine, fat, glucose, and to a very much lesser extent, protein. So substrates then are things that we break down to use for fuel. So high intensity, short duration, ATP phosphocreatine, low intensity, long duration, that's the aerobic energy system, and kind of that middle ground, so 2 minutes or less of all out, that is the glycolytic energy system. So the second bullet point on there, with training, tailored to the energy demands of a particular sport, our ability to use those energy systems improves, right? And so if we do repeated sprint training, we can store a little bit more ATP, we can store a little more phosphocreatine. So you'll have higher fuel storage, you'll have more substrates that you're going to use during training. Same kind of thing with both strength training and to some extent with endurance training. You're going to see increased storage of glycogen, so intramuscular sugars, to provide, again, a substrate of fuel to regenerate ATP. So with training then, we can improve the use and improve the storage or increase the storage of the substrates and then improve their use. And so that concept of training certain energy systems, so the glycolytic system, the oxidative system, ATP phosphocreatine, that is called metabolic specificity. So I'm training a particular energy system that is probably the primary energy system that I use in a given sport. All right, so there's a lot of, at the outset, a lot of definitions on here. So in terms of bioenergetics, what that means, that's the flow of energy in a biological system. So that involves the conversion of macronutrients into biologically useful forms of energy or usable forms of energy. So remember that the macronutrients are things from which we derive calories. So those include things like carbohydrates, fat, and protein. And so basically what we're going to do, all those things contain energy in their bonds, right? In the shape of the molecule and the bonds between the atoms of that molecule, there's energy to be found. And if you split those bonds, that gives off energy. But with a molecule like glucose, for example, there's so much energy in there that if we split all those bonds at one time, it would give off too much energy, and that could potentially damage the cell that split that glucose. And so what we have to do is to do that in a very stepwise fashion. So we do that in the case of glucose over a series of 10 steps of glycolysis, right? And so by doing it in those small increment, or making those small incremental changes to the molecule, we release a little bit of energy at each step, and then we eventually are going to use some of that energy to help us remake ATP. So to convert that then into a useful or usable form of energy for the muscle cell. Catabolism is breaking down. So if something is catabolic, we're breaking down. So for example, if you are fasted, if you haven't eaten in a really long time, so let's say 12 hours or more, you can be fasted in less time than that, but let's say for sure if you haven't eaten in 12 hours, you're considered fasted. So if you're just in a fasted state, or if you're exercising fasted, then you would be catabolic, right? You're going to be breaking down because you need fuel. Let's say you're exercising fasted. You're going to need fuel for that exercise. And so what you're going to do then is to break down glucose, or glycogen in this case, inside of the liver to keep your blood glucose up. You're going to break down glycogen inside of the muscles that are being exercised to fuel muscle contraction. So all of that is catabolic. You're breaking down sugar inside the muscle, you're breaking down sugar inside of the liver. And then if you deplete those stores, or even to some extent really before you do, if you're exercising in a fasted state, you're going to actually break down the muscle tissue to try to convert some of those proteins into glucose. So we can convert protein into glucose via a process called gluconeogenesis, and that happens primarily in the liver. So that would be another catabolic reaction. So if we're engaged in an exergonic reaction, that means that we are going to give off energy. We're breaking something down, and as a result of that, that's probably going to give off energy. Anabolism, or anything anabolic, on the other hand, is the opposite. So if we are anabolic, we are building things, right? So if you are taking anabolic steroids, because that's probably where you've heard the term the most frequently, right? So anabolic steroids are synthetic hormones that mimic testosterone, and so what they do is they promote, they do what testosterone does, but among the things that testosterone does is to promote muscle protein synthesis. So they promote muscle growth. So they are anabolic because they're tissue building. But you're also in an anabolic state after you, let's say, exercise, and then you consume carbohydrates and protein after you work out, right? So you're probably familiar with the various like milk ads. You want to have chocolate milk after you exercise, or various recovery drinks, or those kinds of things. And the idea is to shift the body from being catabolic, so from a state of breaking down, trying to free up energy, to a state of anabolism. So you're trying to build back up. You're trying to repair the muscle. You're trying to replenish your ATP phosphocreatine stores, those kinds of things. So when we're engaged in endergonic reactions, we're going to build up, as you're going to see it today, when we talk about endergonic reactions, we're primarily going to be talking about ATP and phosphocreatine. So if you split ATP to give off free energy into adenosine diphosphate and a free phosphate, then that's going to be an exergonic reaction that splits it. And then we're going to use other fuels like carbohydrates to rebuild that ATP, to push that phosphate or bond that phosphate back onto the adenosine diphosphate to remake ATP. That's an endergonic reaction. We're building that molecule back up. So what we do then is we break down foods, so macronutrients, so carbohydrates, for example. Those are going to undergo a series of catabolic or exergonic reactions. We're going to break them down. And then we're going to use those exergonic reactions to drive endergonic reactions, to drive the reactions of building ATP back up, restoring ATP. And then metabolism is the total of catabolic and anabolic reactions in a biological system. All right. So on the last slide, I was kind of assuming you knew what ATP was, and you hopefully do at this point. But if not, just a quick review here. So adenosine triphosphate, that is the energy molecule. It is the molecule that we split, and by splitting that molecule, the energy given off directly drives muscle contraction, right? So it allows transfer of energy from endergonic, so a stored energy form, to exergonic. We're going to break it down, and that'll give off then free energy. In terms of the graphic you're looking at up here, so here's our little adenosine backbone. here's one little phosphate, there's the P. Here's our second phosphate, and then here's our little third phosphate group. And these things that look like beans with electricity in them, that one is a high energy bond, and then that one's a high energy bond. And so when we split this last phosphate off, that gives free energy. And again, that free energy is going to be used to drive muscle contraction. Really what it does is it resets those myosin heads into that cocked or ready position so that when they see the active sites or the binding sites on the actin, they're able to jump up and attach and pull it toward the midline. So ATP breakdown is known as ATP hydrolysis. So hydro means water, lysis means cutting, so hydrolysis or hydrolysis means cutting with water. And so we're going to use water in that process of breaking down ATP. The enzyme that breaks down ATP is called ATPase. In muscle cells, we're going to use myosin ATPase. That's going to be the enzyme that's actually going to break down ATP to reset that myosin head. That's your myosin ATPase. As an aside, that differs between different types of muscle fibers, so type 1 versus type 2, and then there's subcategories. Those will have different types of myosin ATPases in them. That's part of the reason they stain differently. If you look at a cross-section of a muscle that has different colored muscle cells, the reason for the difference in staining, one of them, is the differences in myosin ATPases. Other ATPases, so there's a calcium ATPase and then a sodium-potassium ATPase. So that's going to help drive the sodium-potassium pumps. The calcium ATPase will drive the calcium pumps in the sarcoplasmic reticulum. Other things, and I'll try to really enunciate when I say this, ADP, adenosine diphosphate. So here, going back to the top right, so again, our little adenosine backbone, 1, 2, 3 phosphates. So if you split off this last phosphate, give off free energy, now what you're left with are 2 phosphates. So then the remaining molecule is adenosine diphosphate, because we're left with, remember, di is 2. So we're left with 2 of those, right? So that's your adenosine diphosphate. And then if we split this other high energy bond here, then what we're left with is adenosine monophosphate. Mono meaning 1, like a monorail only has 1 rail. And so that little adenosine backbone only has 1 phosphate attached to it, so that's adenosine monophosphate, or AMP. Now, while we can split off that second phosphate, the body prefers not to do that. It can, but it prefers not to because there is more energy in this bond than there is in this one. So we'd rather make an adenosine diphosphate and a free phosphate and reassemble that molecule, but if need be, for a really an extended sprint, let's say, you can split off that second phosphate group and make an adenosine monophosphate and then have 2 free phosphates. All right, so 3 basic energy systems then exist in mammal cells to replenish ATP. There's the phosphagen system, and so one of the things I'm trying to do in this class really is I'm trying to follow the book really closely and use their terminology, which is probably a little bit different than the terminology I've used with you in previous classes. So the phosphagen system then includes ATP phosphocreatine, and the way that it's going to be included in the questions is as the phosphagen system, so just something to get used to as you prepare, hopefully to take the CSCS exam. And then the second one is glycolysis, so that means to break down glucose in the absence of oxygen. And then there's the oxidative system. So we can, or we do, break down glucose. Eventually the products of glycolysis actually go through the oxidative system, but glucose first has to go through glycolysis, and then if there's oxygen available, the products of it go through the oxidative system. So anything aerobic means that it involves oxygen. Anything anaerobic is without oxygen. And so the top 2 then, the phosphagen system and glycolysis, both of those are anaerobic processes. So both of those 2 can result in replenishment of ATP via anaerobic processes. We can replenish ATP without oxygen in those cases, or in those systems. On the oxidative side, or in the oxidative system, we obviously need oxygen, so that's going to be aerobic. All right, so the phosphagen system. So that's ATP phosphocreatine. So again, it's going to provide energy for short-term, high-intensity activities, things like sprints, vertical jumps, lifting weights, anything really short, powerful bursts. That's going to use the ATP phosphocreatine system. Another thing, just to make life complicated, as we'll talk about later on in this lecture, is that at the start of exercise, the ATP phosphocreatine system is always active. So if you leave class, when you go from resting to moving, you are going to rely on the ATP phosphocreatine system in the muscles that you're using. So whether you're pushing or walking or running, however quickly you want to leave class, you're going to use the ATP phosphocreatine system in those working muscles because it takes a little while to increase oxygen delivery to the muscles. So it takes a little while. There's some lag time in ramping up the oxidative system. And so in that interval, before we get the oxidative system ramped up, we're going to then rely on the anaerobic system, or the ATP phosphocreatine, the phosphagen system. So as mentioned, this is the primary system that we use for all-out efforts of give or take 10 seconds. So when I was first learning this, and I've probably told you this story before, but oh well, years ago now, like 20 years ago, I was like, well, if ATP phosphocreatine can produce so much energy so quickly, why don't we just use that all the time? And the answer is because both ATP and phosphocreatine are really heavy molecules. And because they're so heavy, you can't store very much of them. And so the other thing that makes them a little bit heavier is that with both of them, when they move inside of a cell, thinking back to what we talked about in 202, when we talked about cells, those large molecules inside of the muscle cell are then going to pull water with it, right? So they're going to create an osmotic gradient. And so they're going to pull water with them. So the body can store about 80 to 100 grams of ATP at any given time, which is only about 3 ounces, so that's pretty small. During all-out sprints, the amount of ATP in a muscle cell can decrease by 50 to 60%. We don't typically deplete it though, because we still need ATP not only for muscle contraction, but we also need ATP to run sodium-potassium pumps, to run calcium pumps. So it does other things than fuel muscle contraction. So it would be pretty unusual to completely deplete ATP inside of a muscle cell. The stores of phosphocreatine relative to ATP are 4 to 6 times higher, so we store a lot more phosphocreatine, but again, it's still a pretty big, heavy molecule, in muscles. It makes them heavier. So phosphocreatine, still a big, heavy molecule, and so because of that, we can't store all that much of it. So the example I usually give here too, I don't know how many of you are familiar with supplementation with creatine monohydrate or any of the other forms of creatine. Whenever the muscles take up that creatine, it again pulls water with it, and so typically the way that creatine is supplemented is you take 5 grams at a time, 4 times a day, so about 20 grams a day for about a week. And so when you do that, that's called loading, and you only do it for about a week. But at the end of that loading week, the muscles are saturated with creatine, and most people typically gain somewhere in the neighborhood of 3 to 5 pounds by the end of that week, and that is all water weight. That is all from the muscle cells becoming saturated with creatine and then pulling water with it inside of the muscle cells, causing the muscle cells to be a little bit more swollen. So that's the ATP phosphocreatine system, or the phosphagen system. Continuing with the phosphagen system, so I mentioned this a minute ago, the adenylate kinase reaction. So that is where we have 2 adenosine diphosphates, or ADP, and then we'll use this enzyme, adenylate kinase, which is also known as myokinase, and that will pull a phosphate off of one of these ADPs, and then we're left with one adenosine triphosphate, or an ATP, and then an adenosine monophosphate. And the reason that reaction matters, again, we prefer not to do this, but certainly we can during all-out efforts. And the reason that matters is because adenosine monophosphate is a powerful stimulant of glycolysis. So it's going to turn on the next energy system, or basically it signals, hey, we're running out of ATP, or our stores are running low, we got to turn on the next system. So that's glycolysis in terms of the next fastest and the next most powerful system next to the phosphagen system. Speaking of glycolysis, so this is a graphic you've seen before in 201 or 202, maybe both, probably for sure in 202. So this graphic, there's a couple parts to it, but this is the depiction of glycolysis. So glycolysis is the anaerobic breakdown of glucose, right? So glucose is sugar. So we can ingest other kinds of sugars, things like fructose, right? But for the most part, we actually convert those to glucose. So here's our little glucose molecule at the top. It's a little 6-carbon ring, okay? So it's a nice little ring shape. And so the first thing we're going to do, we're going to take it inside of our muscle cell. So we've crossed the muscle cell's membrane here, and then we've actually used an ATP when we brought that inside of the muscle cell. And so what that does, the addition of that little phosphate group, and we end up with, this is our product here, glucose 6-phosphate, so that phosphate that we added is on the 6th carbon. So we end up with glucose 6-phosphate, and now that little glucose is stuck inside of our muscle cell. So once glucose is inside of a muscle cell, we don't have the enzymes in muscle cells for it to leave, so it's stuck there. The muscle cell has to use it. That's as opposed to in the liver, when we move glucose inside of the liver, we actually have an enzyme in the liver that allows us to remove that phosphate group and kick it back into the bloodstream. And so we use liver glycogen to keep our blood glucose elevated, so during an overnight fast or during a several-hour fast. And then we use muscle glycogen to fuel muscle contraction. So one of the ways that this is often described is that muscle cells are selfish, meaning that once they get that glucose, they have to use it. They can't give it up. And why that matters is if you're engaged in either an exclusively upper body type of exercise or exclusively lower body type of exercise. Let's say you're riding a lower body bike or riding an upper body bike. You can ride that bike for a prolonged period of time, and you can deplete the glycogen, the sugar stores inside of, let's say we're doing the upper body bike, inside of the upper body musculature, in triceps and biceps and pec major, in your upper traps, those kinds of things. And then you might think, well, okay, so depleted the glycogen there, I can just give up glycogen for my legs because they're not moving, and then that'll help fuel the muscle contraction in the upper body. But as I mentioned a second ago, that can't happen. So even though you'll still have plenty of stores of glucose or plenty of stores of glycogen inside of the lower body musculature, they can't give it up. They can't contribute to the cause. Because again, the way it's usually described, muscle cells or muscles are selfish. So once we've done that, if we are not using energy, then we can make that little glucose 6-phosphate with a phosphorylase enzyme. We can transform that into glycogen. But let's say we are using energy right now. So then we're going to proceed to step 2, onto this enzyme, then on to, so after this enzyme does its work, now we end up with a fructose 6-phosphate. Then we use another ATP, so we've given up more energy, so we've actually burned 2 ATPs by step 3. And so when we do that, we end up with a fructose 1,6-diphosphate. And so what that means then is that, well, number one, the shape of the molecule has changed. That's why it's fructose, not glucose. But number 2, you have phosphates on both the 1st and the 6th carbon. So that's what that means. So basically we have a symmetrical molecule here, and that's going to matter in a second. And so the enzyme that modulates that reaction, that is phosphofructokinase, or PFK for short, and that is one of the important what's called rate-limiting enzymes of glycolysis. So it's one of the ones that if it's not available, then we can't proceed with glycolysis. So that's how quickly you can churn through glucose anaerobically is dependent upon the action of phosphofructokinase, or PFK. So if you ever see a question about what's the rate-limiting enzyme related to glycolysis, the answer they're probably fishing for is PFK. So the next thing we're going to do at step 4 is to split this 6-carbon molecule into 2 3-carbon fragments. That's what's happened here at 4. So you got 1 3-carbon fragment going this way, 1 3-carbon fragment going this way. So the ADALase enzyme did the splitting. Got another enzyme here, 3-phosphoglyceraldehyde on each side. Now what we're going to do is we're going to use an NAD, so that's a niacin or B vitamin derivative, and we're going to pull a hydrogen off of this molecule, and so the NAD gets reduced, and so it is going to end up as an NADH. So you got one of those on each side, so we have an NADH produced on each side. Go down to the next step. And so finally at step 7, we're going to get back an ATP, right? So we get back an ATP on this side, we get back an ATP on this side. So we've made 2 ATPs, but we had to put in 2 at the beginning of the process, so we're still at a net 0. Put in 2, got back 2, our bank account's still 0. Then we're going to go to the 8th enzyme, the 9th enzyme, the 10th enzyme, finally we get 2 more ATPs. So at the end of glycolysis then, we have a pyruvate, and we've gotten back 2 ATPs. So the end product of glycolysis is pyruvate. There's 2 pyruvate molecules we end up with. And then we've generated 2 ATPs, or we've netted 2 ATPs. We actually made 4, but we put in 2. So we net 2 ATPs, and then we also have created 2 NADHs. So all of this stuff, and I should have emphasized this earlier, but I'm thinking about it now. So all of this stuff that I've been describing to you between the phosphagen system and the glycolytic system, again, both are anaerobic, but all of this happens in the cytosol, or the sarcoplasm of a muscle cell. So all this happens outside of the mitochondria. All the anaerobic stuff happens outside of the mitochondria. So then what we're going to do, if there is oxygen available, because let's say we're working at a low intensity, and so we can deliver enough oxygen to the muscle cell, it can diffuse inside of the cell and go into the mitochondria. If there's oxygen available, then this pyruvate is going to go inside of the mitochondria, as is this one, and then as are these NADHs. If there's not oxygen available, so if I'm working at a higher intensity, let's say I'm sprinting, let's say I'm running the 800-meter dash, right? So something that's going to take somewhere in the neighborhood of 2 minutes if you're moving really fast. So if we're doing something like that, it's an all-out sprint for about 2 minutes, then we're using ATP faster than we can deliver oxygen to the muscle cell. And so because I'm not delivering oxygen fast enough, what we're going to do, instead of taking these NADHs to the mitochondria, we're actually going to take, these NADHs are going to go down to the bottom here, to pyruvate, and they're going to drop their hydrogen onto pyruvate, and they're going to make lactate. And so by dropping that hydrogen onto pyruvate to make lactate, then that now NAD plus can go back and we can continue with glycolysis. So that allows us essentially a temporary storage site for those hydrogens so that we can continue with glycolysis. Because otherwise, once those NADHs or NADs become saturated with hydrogens, then glycolysis has to stop. If we can't continue stripping hydrogens at step 6, then we can't continue with glycolysis, which means we can't continue to generate ATP, and so then we have to stop, right? And so that's a problem. So what we'll do then with this lactate is we can either shuttle it out of the working muscle cell, so we can kick it out into the bloodstream, and so then it becomes blood lactate. And then it can be picked up by tissues that are not working as hard, so maybe some muscle cells in the upper body, or it can be picked up by the heart. The heart is super aerobic. Its cardiac muscle cells have lots and lots of mitochondria, so it's really good at using oxygen. And so because it's really aerobic, it's really good at breaking down a variety of fuels, including fat, but also lactate. And so that's one of the places that we can dispose of the lactate. So basically what we do then is we take this lactate inside of the, let's say, non-working muscle cell, or the resting muscle cell. We're going to pull that hydrogen off of it, so then that makes it back into a pyruvate, and then pyruvate continues on into the mitochondria. All right, speaking of inside the mitochondria, so again, in saying that we're going inside of the mitochondria now, we're shifting to the aerobic portion of this. And so, yeah, that'll work. So we're shifting to the aerobic portion of this. And, oh, that was the other thing I was going to say, is that we're assuming that there's enough oxygen available. So for the rest of this scenario, I'm describing somebody who's working at not at a very high intensity, right? They're not sprinting. They may be going pretty fast, but they're not sprinting. So now we're going to move from the cytosol inside of the mitochondria. And so our pyruvate then, we're going to pull off another hydrogen, and so it gets converted irreversibly to acetyl-CoA. And then acetyl-CoA goes through another 10 steps, 11 in total, counting this first one, but it goes through another 10 steps, again 11 in total. And over the course of those steps, we're going to pull off some more hydrogen. So you can see here at, between step 4 and 5, we're going to pull off a hydrogen. We're going to pull off another hydrogen here. We're going to remake one ATP here, pull off another hydrogen, pull off another hydrogen. So the citric acid cycle, and in the book and in some of the NSCA materials, you'll see it still referred to by its older name, which is the Krebs cycle. So the Krebs cycle and the citric acid cycle are the same thing. So sometimes you'll see CAC, which stands for citric acid cycle, or just Krebs cycle. So they're both, know that they're the same thing. So basically what happens with the citric acid cycle, the important things to know then are that the products of it are lots of hydrogens, so NADHs and FADHs, but also that we do make one ATP, and then this is where carbon dioxide is given off. So one of the things I talk about in classes pretty frequently is that when muscle cells are working, they're going to produce carbon dioxide. And so they produce carbon dioxide during the citric acid cycle. And so then we have to get rid of that carbon dioxide, which we do by kicking it into the blood, and then we breathe it out, right? So we make all these NADHs, and then what we're going to do, remember that the mitochondria has two membranes, right? So there's this outer membrane out here and an inner membrane in here. And inside of the inner membrane, you have this cytochrome complex. And so this is where we get into the electron transport chain. So I mentioned earlier that if a molecule accepts electrons, then it is reduced. So when NAD becomes NADH, it is accepting electrons attached to hydrogen, but in doing that, it is then reduced. When it gives them up, it is being oxidized. So NAD gets reduced to NADH, and then it gives up those hydrogens, and so it becomes oxidized. Once it's oxidized, it can go back and pick up more hydrogens, so it can be reduced again. So that's the coupling of oxidation reduction reactions. So we can give up electrons and accept electrons, give up electrons and accept electrons. So what will happen then is whenever the NADH drops off its hydrogen, we actually pull an electron off of it. And when we do that, that electron then gets shuttled between these different complexes, which is way more than you'll need to know for the NSCA. But as the electrons get shuttled from one complex to another, that gives off a little bit of energy. And that little bit of energy is enough to allow us to pump hydrogen into this inner membrane space. Okay? And so in here, we've got lots of hydrogen because we've pumped it as we strip off these electrons. Then what we're going to do is we're going to allow hydrogen to move with its concentration gradient. So it's going to go from high concentration in the intermembrane space to low concentration inside that inner matrix. And when it does that, it's going to spin this complex, this ATP synthase complex, and that spinning of the complex as hydrogen flows back through that protein, it's going to change shape, and that spinning or changing shape of the protein we use to reattach a free phosphate to an adenosine diphosphate. So it remakes ATP. And so that's what you got pictured here. So you got an adenosine diphosphate, free phosphate, hydrogen's going to come through, and then when it does, that turning of the molecule puts those two back together, and we have a new ATP. Then we have to get rid of our hydrogen. And so what we're going to do is we're going to attach that hydrogen to oxygen, and then that's going to make metabolic water. And so then that's how we get rid of those hydrogens. As part of this process, again, more detailed you need to know, but we'll reattach the electron that's come down through the electron transport chain as well. So that's where oxygen comes into this process, is we have to get rid of all these hydrogens that we've pulled off of what started as glucose, or what starts as fat, or what starts as a protein. So we strip off these hydrogens, we use those hydrogens, we actually pull the electrons off of the hydrogens to pump hydrogens into this intermembrane space to create a gradient, and then we allow hydrogen to flow with its gradient. That produces metabolic work that allows us to remake ATP. So that's the oxidative side of things. But again, the oxidative side of things is dependent upon the ability to supply oxygen and get it inside of the mitochondria so that we can attach it to those hydrogens. If we're running through ATP so fast that we can't get oxygen to the muscle cell, inside of the muscle cell, then inside of the mitochondria, then we have to use the anaerobic system. So we have to use phosphagen and we have to use glycolysis. There was something else I was going to say about that, and I've forgotten for the moment, but that's okay. And there's a little ATP synthase, a little close-up there, and all the steps that happen with that. All right, so the key points then, just in case I'd missed them as I was going along. First, that glycolysis and the phosphagen system, when we break it down, both of those two occur in the sarcoplasm, right? So in the cytoplasm of the muscle cell. The end product of glycolysis is pyruvate. Glycolysis itself, with its 10 enzyme-mediated steps, is anaerobic. Some books, including the NSCA's book, refer to that as fast glycolysis, which I think is unnecessarily confusing, but that's what they do, so that's how we'll call it. Because the reason I think it's unnecessarily confusing, glycolysis itself, always anaerobic. So to call it anaerobic glycolysis or fast glycolysis, it always operates at the same basic speed. So anyway, glycolysis itself is anaerobic, also known as fast glycolysis. When we work at lower intensities, those hydrogens that we pull off that I showed you are going to go into the mitochondria, attached to oxygen to make water. And then so if the end product of glycolysis is ATP and metabolic water, then that's slow glycolysis. If the end product of glycolysis is we got this pyruvate, and in order to keep this process up, because we're working at a high intensity, we have to drop hydrogen onto it to create lactate. Now that's anaerobic, or in some textbooks, anaerobic or fast glycolysis, okay? So if we're working at higher intensities, hydrogens can be temporarily attached to pyruvate to form lactate, which we talked about, and that allows glycolysis to continue. Here's a key point, and I'm sure there's questions in the bank about this. So lactate itself is not the cause of fatigue. So the cause of fatigue is a buildup of hydrogen ions. Okay, so that's proton accumulation, right? And so why hydrogen is produced is because when we hydrolyze ATP, so when you break down ATP using water, that gives off a free hydrogen as well. So as we give off a bunch of free hydrogens, that makes the inside of the cell more acidic. And so in terms of pH, the lower the pH, the higher the acidity. The higher the pH, the more basic the solution. So as we generate a bunch of free hydrogens when we hydrolyze ATP, that gives off a bunch of free hydrogens, as I just said, a little redundant, but that makes the inside of the cell more acidic, so it lowers the pH. As the pH comes down, then we get an inhibition of glycolytic enzymes. So all those little steps I showed you, the different enzymes like PFK, those get inhibited when the inside of the cell gets too acidic. It also inhibits the binding of calcium to troponin C, which then inhibits muscle contraction. And then it also, in some other way, may interfere with cross-bridge cycling. So that decrease in intracellular pH is referred to as metabolic acidosis. So as the inside of the cell gets more acidic, that's metabolic acidosis, again, caused by breaking down ATP, giving off free hydrogens. The lactate can be transported to the liver, where it can be converted to glucose, or the lactate, as mentioned, can go to resting muscle cells or the heart, which is that last little point there that can be metabolized. And then I have my but wait. So again, there's probably a question about whether or not lactate causes fatigue. No, the accumulation of hydrogen inside of the cell causes fatigue, but lactate is related to fatigue. It correlates with fatigue because if you're working at higher intensities, again, you're running through ATP faster than you can supply oxygen, so you have to make lactate. And that means, of course, that you're running through lots of ATP, so you're giving off lots of hydrogen. So those two things are coupled, if you will. I guess coupling is not the most accurate description of them, but those two things are correlated. Those two things generally go together. So as you're running through a bunch of ATP, you're creating a lot of hydrogens. Because you're running through ATP so fast, you can't possibly supply oxygen fast enough, and so you have to make lactate. So those two things are related to each other. And so the accumulation of lactate indicates the production of hydrogen at a higher rate than they can be disposed of aerobically, and increased muscular acidity, which induces fatigue. So because of that, measures of blood lactate are still useful as predictors of fatigue because that tells us that we are using ATP at a faster rate than we can dispose of those hydrogens aerobically. All right, other things. So glycolysis is stimulated by increased adenosine diphosphate, because that means we're breaking down ATP. Increased free phosphate, you also see that as PI, breaking down ATP. Increased monophosphate, breaking down ATP. And then decreased pH, giving off hydrogens. So glycolysis is stimulated by all of these things, adenosine diphosphate, free phosphate, adenosine monophosphate, that indicate we're breaking down ATP, as does the decreased pH, because it's caused by the release of free hydrogens. Glycolysis is inhibited or slowed down or stopped by plenty of ATP. If I have lots of ATP available, no reason to keep breaking down glucose to remake it, right? If we have full stores of creatine phosphate, you'll also see that one abbreviated as PCR, which means phosphocreatine. So I have full stores of phosphocreatine or creatine phosphate. I don't need to break down glucose. Citrate, which was in the citric acid cycle. Free fatty acids, markedly lower pH. Oh, okay, I get where I'm going with that. So markedly lower pH. So if the cell inside the cell is really, really acidic, then that's going to stop glycolysis. Because if the inside of the cell gets too acidic, right, that can cause damage to the cell's membrane, can cause cell death. So there are breaks on this situation. As mentioned, phosphofructokinase, PFK, is the rate-limiting step, comes in at step 3, and it commits the cell to metabolizing the glucose instead of storing it as glycogen. So it can't go backwards after we go through step 3. All right, so let's talk about lactate threshold. So as you can see there, the lactate threshold is the exercise intensity at which blood lactate begins an abrupt increase above baseline concentrations. And so when we start to see an increase in blood lactate, it's because we're working at an intensity that is higher than, or viewed another way, we're running through our ATPs faster than we can deliver oxygen to the muscle cells to get rid of those free hydrogens aerobically. So it's related to what we were just talking about for the last several minutes. So we're seeing an increase in blood lactate because of the intensity of the exercise, because it's higher than our ability to deliver oxygen to the working muscle cells. A related term, so lactate threshold is abbreviated LT, and a related term is the onset of blood lactate accumulation, or OBLA. And so that occurs when blood concentration of lactate reaches 4 millimole per liter. And that inflection point, so you're going to see it on the next slide, I'm going to show you a graphic of this. That inflection point probably represents the recruitment of type 2A and type 2X motor units. So we're starting to get into some of those larger, faster motor units. But because they're larger and faster, they rely more on anaerobic systems, and so they're going to generate more lactate, and so you're going to see this big inflection point where the lactate really starts to accumulate very quickly. So that's the onset of blood lactate accumulation. So in untrained individuals, lactate threshold is typically somewhere around 50 to 60% of aerobic capacity, or VO2 max. In trained individuals, lactate threshold is more like 70 to 80% of their VO2 max. So if you are aerobically trained, you can work at higher intensities and not accumulate lactate. And the reason for that, there are several, but one of the primary reasons for that are the ways that muscle cells specifically, adapt to endurance training. So muscle cells that are endurance trained have more capillaries, so they have a greater area to diffuse oxygen into the muscle cell. They have more mitochondria, so more spaces or more places to use that oxygen, and then they have more of the enzymes of the citric acid cycle. So an aerobically trained muscle cell is able to more effectively get oxygen into the muscle cell and to more effectively use oxygen inside of that muscle cell. And so because you can use oxygen more efficiently and more effectively, you don't accumulate lactate until a higher intensity. So one of the questions in the test bank, or the quiz bank for this, asks about the effect of aerobic training and what it does to lactate threshold. And what it's looking for is it shifts it to the right. So it shifts it, and based on this diagram here, click over, there we go. So it's going to shift it to a higher percentage of your VO2 max. That's what we mean by shifting it toward the right. So you can work at higher intensities and not accumulate lactate. So for example, that's why your really elite marathon runners can run at 80% and higher of their aerobic capacity and still not generate lactate. It's because of the adaptations that the muscle cells have made that they can use oxygen that much more effectively. And also the heart is more effective at delivering oxygenated blood to those muscle cells. So what you're looking at here is a person who's probably, just based on the data, I was kind of mathing it out before I started recording the presentation. So based on the data there, the person here has a max heart rate of 182, so they're probably somewhere in their mid to late 30s and moderately but not highly trained. So their onset of, their lactate threshold is around 50% of their max heart rate. So their lactate threshold is here. And so their max heart rate, there we go, is over here. So their lactate threshold is somewhere around 50% of their max heart rate, but it's at 65% of their VO2 max. So you can see that line's a little more obvious. So they're at 65% of their VO2 max. So again, a little bit better than untrained, but not great. And then their onset of blood lactate accumulation, so the point at which it reaches 4 millimolar here, is at 68% of their heart rate max, and then 85% of their VO2 max. So there's those 2 points. So thing to know, if you are working above your lactate threshold, you're working at a higher intensity than you're able to, you're running through your ATP faster than you're able to deliver oxygen to get rid of those hydrogens. And so some lactate is accumulating, but we refer to it as onset of blood lactate accumulation when we hit this absolute point of 4 millimole per liter. All right, so on the aerobic system side, so the aerobic or the oxidative system, that's our primary source of ATP at rest and during low intensity activities. The oxidative system primarily uses fat and carbohydrate. So when we're working at low intensities, we primarily use fat. When we shift to a little bit higher intensities, we're going to use carbohydrate. One thing to know as well is that protein is not a major energy source. The times when protein becomes an energy source for exercise is during really prolonged exercise. So you can see they're greater than 90 minutes. So like running more than a half marathon and you're not fueling, like you're not consuming Gatorade or gummies or things like that, or you're not starving, then you're not going to use protein for energy. But if you meet those criteria, if you're exercising for hours on end, then you're going to start to break down some protein, and then that can become an energy source. Typically it's pretty small, so usually it's somewhere in the neighborhood of 3 to 5% of your fuel, but it can increase up to just shy of 20%, again with really prolonged exercise or starvation. In terms of the control of the aerobic system, so again, it's going to rely on the availability of NAD+ and FAD2+. So the niacin, again, a B vitamin derivative electron carrier, and then the FAD is a riboflavin, which is another B vitamin derivative, and that's an electron carrier as well. Having said niacin and riboflavin, so that's part of the reason that in different energy drinks and certain types of like performance vitamins, and I'm doing air quotes as I say that, they're going to have really high doses of B vitamins, and they talk about how that helps you make energy. And so the thought is that if you're deficient in those B vitamins, if we supply you with lots of niacin or lots of riboflavin, then that'll allow you to make more of these electron carriers, that'll allow glycolysis to function more effectively, and that'll allow the oxidative system to function more effectively. So that's the basic rationale. That's why there's such high doses of B vitamins in those things, is because of the role of a couple of them in glycolysis and in the citric acid cycle. That said, don't go out of your way to take lots of them, because too much can also be bad, as always. Niacin can result in like flushing of the skin if you take it in too high of doses, so you don't want that. I hear it's pretty uncomfortable. I actually knew a student once who, I don't remember what she was using. It was some supplement. This was probably 10-ish years ago, but she was using a supplement that had really high doses of niacin in it, and she ended up looking really flushed, and she said basically she had kind of hives and was itching all the time because of it. So anyway, once she stopped the supplement, it went away. And then isocitrate dehydrogenase, which is one of the ones in the citric acid cycle. Energy release from fat. So fat, most of the fats that we use are triglycerides. So there's a little glycerol backbone, and then these long chains, these long carbon chains of fatty acids. So there's 3 fatty acids. So it's triglyceride because you got the triglycerol backbone and then 3 fatty acids hanging off of it. What we'll do then is we'll actually break off one of the fatty acids to start with. And then because, again, it's this long chain of carbons, we'll actually chew off the carbons 2 at a time in a cycle called beta oxidation. So in beta oxidation, we'll break those fatty acids down into little 2-carbon fragments. Those 2-carbon fragments become acetyl-CoA, and then it goes through the citric acid cycle that we just talked about. And so, with most of the triglycerides that we break down for energy, those carbon chains are give or take 18, 20 carbons long, and so you're going to get 9 or 10 of those molecules per fatty acid chain. So you get 9 or 10 little acetyl-CoAs per acid chain, and then you've got 3 of those fatty acids, and so then that gives you 27 to 30 little acetyl-CoAs that generate lots of hydrogen that then we can generate lots of ATP. So then the little glycerol backbone goes through glycolysis, eventually becomes acetyl-CoA, and then it goes through the citric acid cycle as well. So when we break down the little glycerol backbone, it's going to produce 19 ATPs when we take it all the way through the citric acid cycle and the electron transport chain. When we take the fatty acids through beta oxidation to make acetyl-CoA, and then they go through the citric acid cycle with a typical 18-carbon fatty acid, we're going to end up with 441 ATPs from that, so a total of 460 ATP. As opposed to, I didn't show you the numbers for glucose, but if you fully break down a molecule of glucose, depends on how you do the math, but it's somewhere between 32 and 36 ATPs. So if we break down a molecule of glucose, let's assume the high end, we get back 36 ATPs. If we break down a fatty acid, we get 460 ATPs. So fat is a much more efficient source of fuel. We can generate lots and lots more ATP from fat. But in order to break down fat, we have to go through beta oxidation, and we have to go through the citric acid cycle. We can't use the citric acid cycle and produce a bunch of hydrogens, or NADHs and FADH2s. We can't produce those things if we don't have enough oxygen available. So fat can only be used as a fuel if oxygen is available. Or viewed another way, glucose, sugar, is the only fuel source that can be used, or the only macronutrient, I should say, the only macronutrient. Again, those are fat, carbohydrates, and protein. So glucose is the only of the macronutrients that can be used anaerobically. So that's the big limiter on fat, is it produces tons of energy, but we have to have oxygen in order to make that energy. So that's its shortcoming there. So we use fat then for lower intensity exercise. The other thing, kind of another way to conceptualize this, is that glycolysis, remember, glycolysis in and of itself is only 10 steps. So in those 10 steps, we get back 2 ATP. For the phosphagen system, ATP phosphocreatine, in 1 step, we can remake an ATP, right? And so the phosphagen system, 1 step, 1 enzyme, 1 ATP, that's really fast, really powerful, can fuel high intensity exercise. Now, the glycolytic system, 10 steps, 2 ATPs, so a lot more steps. It's slower, it's not as powerful, but it does generate 2 ATPs. And then on the aerobic side, it generates lots of ATPs, but there's also lots of steps. So each fatty acid chain, if we're using fat, has to go through beta oxidation, then the citric acid cycle, then the electron transport chain. So it produces a lot of ATP, but it takes a long time to do it. And so because of that, it's not as powerful. We can't maintain as high of intensities because we simply can't generate energy fast enough. There's our little fatty acid. So again, here's our little glycerol backbone, our little fatty acid chain. Here's another one, and then you can see the little carbon backbone to it. So proteins, remember about proteins that they are polypeptides. They are these long strings of amino acids, right? And so a protein, so again, protein itself is a long string of amino acids, so you can break it down into its individual building blocks, which are the amino acids, and then the amino acids themselves, we can convert those to glucose, we can convert them to pyruvate, again, the end product of glycolysis, or into citric acid cycle intermediates. So you can see the citric acid cycle here, and then you can see that different amino acids, so things like isoleucine, methionine, valine, I'm not going to try to pronounce that one, those things come in at this step in the citric acid cycle, as opposed to, let's go with asparagine and aspartate, those come in here, phenylalanine and tyrosine come in here, etc. So what we do then is we break a protein down into its individual amino acids, and then we convert those amino acids into various citric acid cycle intermediaries, or things like acetyl-CoA, or things like pyruvate, which is this group down here. So a couple little tables that hopefully are useful for you. So if our event is 0 to 6 seconds, obviously it's pretty high intensity. You're going all out as hard as you can for 6 seconds. That's going to use the phosphagen system. We go a little bit longer and thus a little bit slower. Still pretty high intensity if you're going all out for 30 seconds. So that's the phosphagen system and glycolysis. So again, fast glycolysis just means anaerobic. That the end result is going to be lactate rather than pyruvate going through the citric acid cycle. 30 seconds to 2 minutes. So again, something like 800 meter dash or less. So we're still going pretty fast because we're going all out for 2 minutes. Now we're using primarily the glycolytic system. We slow down, so we're going 2 to 3 minutes. So now you're talking about, something in the neighborhood of a 1200. Then moderate intensity. So now we're going to start to use the glycolytic system, the oxidative system. And then anything longer than 3 minutes, lower intensity, we're going to use the oxidative system. Again, it takes a long time to ramp up the oxidative system. We have to increase heart rate. We have to dilate blood vessels. We have to get oxygen into the muscle cells. And so that process just takes time. So the oxidative system with that lag time takes several minutes to catch up. And then it's kind of a weird way of depicting it, but whatever. So the phosphagen system produces ATPs really fast, but it can't produce very many of them, right? So it only produces like one to one. As opposed to fat oxidation, takes a really long time to do it, super slow, but produces just a ton of ATP, right? So that's what that table is depicting there. Let's see, so we talked about substrates early on. So substrates are molecules that provide starting materials for bioenergetic reactions. Those include phosphagens, the ATP and phosphocreatine, glucose, glycogen, lactate, free fatty acids, and amino acids. If we deplete our substrates, if you deplete your fuel stores, if you empty your gas tank is another way of thinking about that, the athlete is going to experience fatigue. So the classic example of this is, if you know anything about marathon running, that athletes will talk about, particularly if they don't fuel properly during the race, athletes will talk about bonking or hitting the wall, which usually happens somewhere between mile 20 and mile 22. And what's happened there is that they have depleted their glycogen. And so when they've depleted their glycogen, they say they feel like they hit the wall, the exercise becomes lots and lots harder. Even though they're working at the same intensity, it just feels much more difficult. And the reason it feels much more difficult is they've used up their glycogen. They've depleted their intramuscular fuel source, their glycolytic fuel source anyway. And so now they're having to rely on fat. But fat, again, requires lots of steps to break it down. And so the production of ATP is not as quick. And so it feels harder to work at that same intensity. So hitting the wall then reflects glycogen depletion. Phosphagens here, stuff that matters here. So if you're doing like sprint type workouts, depletion of phosphagens, particularly of creatine phosphate, because again, we're not going to completely deplete ATP. So when you just run out of gas on sprint type exercises, so for example, you'll see when people run the 100 meter, they'll kind of slow down on the last portion of it. That reflects depletion of some of the phosphagens. So ATP replenishment takes 3 to 5 minutes. Full restoration of creatine phosphate takes 8 minutes. So why that matters for you is if you're designing an exercise program and you want the highest quality sprints or the highest quality lifts, so if you're doing like Olympic lifts or power lifts, whatever, and you want them to lift as heavy a weight as possible and have really good quality repetitions, you're going to need really long rest periods. So you'll have them do a sprint or a lift, and they can wait up to 8 minutes and then do the next one. If we start to shorten those rest periods, then you're not going to be able to replenish your ATP phosphocreatine system. And because you can't replenish that one, now you rely on the glycolytic system. But because you're relying on the glycolytic system, the energy transfer rate is not as high, can't produce ATP quite as fast, and so they can't maintain the same intensity. So if we had an athlete who was running, let's say, 60-meter dashes and doing them repeatedly, if we had them doing them with 8-minute rest intervals, you'd keep a pretty constant speed. They'd be able to fully recover and get some good high-quality reps in. If we cut that in half and we only have, let's say, 4-minute rest intervals, they're going to deplete their creatine phosphate stores over the course of several of those. And so as a result of that, and switching over to the glycolytic system, you're going to see performance declines. They're going to get slower and slower as they continue into those sprints. Which, if you're trying to exercise the glycolytic system, that's fine. But if you're trying to maximize the quality of work, they're going to need pretty long rest periods. Glycogen, so I kind of alluded to this a minute ago when I was talking about hitting the wall. So you can store about 400 grams in muscle, and then you can store another 100 grams in the liver. So cumulatively, you can store 100 grams of glycogen. Glucose has an energy production capacity of 4 calories per gram. So if we've got 500 grams that we can store at 500 grams that we store at 4 calories per gram, that's 2,000 calories worth of glycogen. And you use approximately 100 calories per mile that you run. It's more if you're a larger person, but give or take 100 calories per mile when you run. And so that's why when people are at mile 20 to 22 usually is when they start to feel really fatigued, is because given the math I just told you, you store about 2,000 calories worth of glycogen and you use 100 calories per mile running. So after about 20 miles, that glycogen's gone. And so that's why people feel like they're hitting the wall. That's why people feel extreme fatigue there. Glycogen stores are influenced by diet and training. If you have a low carbohydrate diet, that'll deplete your glycogen stores. If you have a high carbohydrate diet, that can increase your glycogen stores with training, right? So one of the things that we can do is with higher intensity training that includes lifting or running or any other type of high intensity aerobic activity, not just running, then what you're going to do is in those trained muscles, they're going to store more glycogen. So the other thing I was going to go for there, as I was talking, I was thinking about the concept that a lot of you are probably familiar with of carbohydrate loading. And so what you do with carbohydrate loading, that's an intentional alteration of diet practices and training practices. Basically what you'll do is a week out from competition, you'll start restricting your carbohydrate intake and you'll do this one really long bout of exercise to try to deplete your glycogen reserves. And then you do low carbohydrate diet for the next several days, I think as far into potentially day 4. Then you do switch to a high carbohydrate diet for days 5 and 6. And then what you'll do is the muscles will super compensate. So basically you've kind of tricked the muscles in a way that they essentially see, oh, hey, we don't have any carbohydrates. And then a few days later, oh, we've got plenty of carbohydrates. Let's store as much as we can. So you kind of trick them into storing more than they normally would. So that's glycogen supercompensation. That's the rationale behind carbohydrate loading. Now that said, if your experience with carbohydrate loading is anything like mine, typically it's usually just athletes eating a bunch of like pasta or something the night before competition, which is great. You're going to maximize the stores that you have, but you're not going to super compensate. You have to deplete first to get that super compensation effect. So just as an FYI there. Other stuff on the slide. So restoring your glycogen, that's based on nutrition. So you want to consume between 0.7 and 3 grams of carbohydrates per kilogram every 2 hours post-exercise for up to 6 hours. What's that mean in English? So to find your weight in kilograms, take your weight in pounds, divide by 2.2. That gives you your body weight in kilograms. And so then you multiply, let's go easy, let's go the high end. So whatever your weight is in kilos, multiply that by 3, because that's 3 grams. So you want to consume however many that is. So let's do mine real quick. Hold on. I think I'm somewhere in the neighborhood of 70 kilos, but to put some numbers to this, like I should have before I started this lecture. All right, let's take my body weight. I got my phone calculator here. You can't see it because it's a recording. But let's take my body weight divided by 2.2. Okay, so I'm somewhere in the neighborhood of 79 kilos. And so let's say I want to maximize my glycogen store, so I'm going to consume 3 grams per kilo. So I need to consume 238 grams of carbohydrates every 2 hours after exercise for up to 6 hours, which is a boatload of carbohydrates. So 238 grams of carbohydrates times 4 calories, that's 1,000 calories worth of carbohydrates every 2 hours for 6 hours. So that would be, marathon training. That's when I would do something like that. So unless you're doing really high intensity, high volume type training, I would say you're probably good with the 0.7 to more like 1 gram per kilo. All right. How can bioenergetics limit our performance? So I talked about glycogen depletion limiting marathon performance, but you can see the same thing in things like soccer or basketball, or any of your other interval sprint sports, where you sprint and then you kind of walk and stand, and then you sprint and you kind of walk and stand. So cumulatively, like a soccer athlete may cover 6 miles, potentially more if they're doing lots and lots of running during a game. And so that then can result in glycogen depletion. Other things, metabolic acidosis. So that's, again, you're running through ATP too fast, giving off too much hydrogen inside of the cell. The pH gets too low, and so that then shuts down the glycolytic system. That interferes with cross-bridge formation, etc. And so then that's going to result in a decrease in performance. Increases in intracellular phosphate, adenosine diphosphate, and ammonia. Related to metabolic acidosis, and then impaired calcium release from the sarcoplasmic reticulum, which again, probably also related to metabolic acidosis. Limiting factors related to bioenergetics. So for a marathon, so if you're running 26 miles, again, the way they do this is weird. So 5 is the most probable limiting factor, not 1. Seems like it'd be 1, but it's not. I don't know. Anyway, so for marathon, muscle glycogen is the primary limiting factor. ATP phosphocreatine stores don't really play into it. For discus, nothing bioenergetically is limiting your performance. So I thought it was funny they stuck it on here. And then let's say for a 100-meter run, so ATP phosphocreatine stores are the primary limiter. And then things like glycogen, fat stores don't really matter. All right, let's talk about aerobic capacity and anaerobic contributions. All right, so maximum oxygen consumption, aka VO2 max, aka aerobic capacity. So they all mean the same thing. So maximal oxygen consumption, VO2 max, and aerobic capacity are all the same thing. So they are a measure of your ability to deliver and use oxygen. And so I use that terminology deliberately because that's what really helped me understand the concept of aerobic capacity. So your aerobic capacity is dependent upon the ability to deliver oxygen to the working muscles. And the ability to deliver oxygen to the working muscles is dependent upon the heart's ability to circulate that oxygen. So, because there's no change in lung structure or function in response to endurance training or response to training more broadly. Your lungs don't change; they just are where they are, unless you smoke or something. But they don't adapt to training, is what I'm going for here. But the heart does, and so the heart becomes a more effective pump, so it can deliver more blood more quickly in response to training. And you have a slightly higher blood volume, and you have, as part of that blood volume, you have a slightly higher number of red blood cells. So between those things, you can deliver more oxygen more quickly to the working muscles. The working muscles, for their part, have to be able to use that oxygen, so they have to have those adaptations I talked about earlier. They have to have more capillaries, more mitochondria, more myoglobin, more citric acid cycle enzymes, all those things. And if they do, then the muscle cells themselves can use oxygen more effectively. And so the result is you can produce more energy aerobically. So if you have a higher aerobic capacity, a higher VO2 max, what it means is that you can produce more energy aerobically, which means that, like during a treadmill test, you'll be able to consume more oxygen and work at a higher intensity. Oxygen deficit and oxygen debt. So here's a tough concept. So, kind of, right? So oxygen deficit. So at the start of exercise, the aerobic system responds slowly, as we talked about. So some of the energy demand is met through anaerobic sources, primarily the phosphagen system. So again, if I'm going from just sitting in class to now I'm leaving class, the energy demands from the working muscles, so in the arms or legs, have increased right away. But to deliver more oxygen to those working muscles, I have to increase heart rate. There's a little bit of lag time there. I have to dilate the vessels, the blood vessels in the working musculature, and then get the oxygen to diffuse in the muscle cell. Probably have to use myoglobin to bind some of that oxygen to deliver it to the mitochondria. So that takes a long time, relatively. So it takes a couple minutes to ramp up. And so because it takes a couple minutes to ramp up, in that interval before the oxidative system ramps up, we have to use anaerobic sources. And so that is the oxygen deficit. It is using anaerobic sources before the aerobic system ramps up. And then after exercise, you're going to breathe more heavily, and your heart rate is going to stay elevated for a little bit after exercise, trying to get the body back to homeostasis. So trying to use the aerobic energy system to remake some of those ATPs that we burn through anaerobically, to remake some of those phosphocreatines that we burn through anaerobically, to get rid of those lactates, all that stuff. And so that's excess post-exercise oxygen consumption, or EPOC. Used to be called oxygen debt, but now we just refer to it as EPOC. And so what it is elevated oxygen consumption after exercise. And how long you breathe heavily after exercise is dependent upon the oxygen deficit created on the front end. And so that then is based on the intensity of the exercise. So the higher the intensity, the larger the oxygen deficit, which means the larger the EPOC, the excess post-exercise oxygen consumption, after the exercise. But EPOC is also related to replenishment of blood and muscle oxygen, again, ATP phosphocreatine synthesis, increased body temperature, trying to restore body temperature, so you're going to run through more oxygen as part of that process, increased rate of fatty acid cycling, and then increased protein turnover. So I have a couple graphics for you here. And so there we go. Okay. So this is a lower intensity exercise, so they're working out for 15 minutes here. So again, when they go from resting to exercise, then there's this window here where they had to rely on their anaerobic energy sources. But because they're exercising for 15 minutes, that's an aerobic exercise. And so what you see here, what steady state is, because that wasn't defined for you, steady state is where you have the, it's purely aerobic exercise, kind of a way of thinking about it. We can deliver oxygen to the working muscles to dispose of the hydrogens at the same rate that they're created, so we're at steady state. So we're delivering oxygen, we're using oxygen, both of them balance out, now we're at steady state. So until we reach steady state though, until oxygen delivery catches up with oxygen demands, we're going to rely on the body's credit card, the oxygen deficit. So that's the anaerobic system. So again, phosphagens and the glycolytic system. And then after exercise, after we stop, again, heart rate's going to stay elevated for a little while. Breathing rate's going to stay elevated for a little while. And so what we're doing then during that EPOC while we're recovering is all the things from the last slide. Replenishing blood and muscle oxygen, getting rid of or remaking those ATPs and phosphocreatines aerobically, etc. Now, if we work, so this is exercise all out for 1 minute. So it's, you run a 400 around the track, so 1 lap around the track as fast as you can. You're working at such a high intensity, you can never meet the demands of exercise. You can never meet the energy demands by supplying enough oxygen. So the whole thing is going to be anaerobic because you're working at such a high intensity. And so with that, then, the oxygen deficit is higher, right? So we used lots of ATP phosphocreatine, and then, because we went for a minute, basically we depleted the phosphocreatine system, and then we generated lots of lactate, we generated lots of free hydrogens, the inside of the muscles got really acidic, all that stuff. So then after exercise, the EPOC period is longer. So you're going to have elevated heart rate, elevated breathing rate for a lot longer after exercise because you worked so high above your aerobic capacity. So why does any of that matter? The reason that stuff matters is this is why, like if somebody wants to lose weight, kind of the two general approaches are to do low intensity, long duration stuff. So like walking or slow jogging, slow riding the bike. And the thought there is that you're using fat as your primary energy source, and so that's going to help you get leaner, which is true. Like that's good for you. But if you want to really use a bunch of energy, you have to. It's more effective to do repeated sprint type stuff, because even though you're using ATP phosphocreatine in the glycolytic system for the actual exercise, you're using the aerobic system and burning fat here in recovery. So when you go and lift weights and you're sore for a couple days afterwards, that rebuilding process, you're going to have increased resting metabolic rate, which means you're just burning more calories just sitting around in the recovery period of that, which can last 48, maybe 72 hours. So some of those repeated sprints, or if you're familiar with high intensity interval training, which I think may even be on the slideshow, the idea behind that is generating these really big oxygen deficits so that we burn a lot more calories in recovery. If you're familiar with, there's a popular gym chain called Orange Theory, and so I don't go there, but I see ads for them all the time. One of the things they talk about is so it's heart rate based training, but they talk about being in the orange zone or something, the orange zone or the red zone, something like that. But the gist of it is they're using heart rate as a proxy measure to make sure that you're working above your aerobic capacity so that you're burning more calories in the recovery from that exercise. So your EPOC stays elevated longer. All right, let's see, metabolic specificity. We kind of talked about some of this stuff at the beginning. So appropriate exercise intensities and rest intervals can permit the selection of specific primary energy systems, so like the phosphagen system or the aerobic or glycolytic systems, depending on the intensity and duration, and those systems then adapt with training. So most sports are interval sprint type sports. So you've got periods of high or very high intensity work with rest periods. So for something like lacrosse, it would be a little bit of a sprint, and you're going to kind of stand around, maybe jog, throw the ball, stand around, sprint, etc. And so you kind of go back and forth between sprinting and resting. So interval training is where we've got this ratio of work to rest periods. And so depending on which system we want to use, that's going to affect how we structure those work-rest intervals. So again, if we want to stress the phosphagen system, those are going to be short in duration, so typically 5 to 10 seconds, but very high intensity, just all out 5 to 10 seconds, and then they're going to have these really long rest periods. So you may rest again for somewhere between 5 and 8 minutes on these. Then the glycolytic system, so we're going to run or we're going to work for a little bit longer, so 15 to 30 seconds of work, and then we'll have, let's say we had 15 seconds of work, there's our work, and then so we'll rest for 45 seconds, something like that. So that stresses then that anaerobic glycolytic system, which again, glycolysis is always anaerobic, but that fast glycolysis system. And so if we want to start working on the oxidative side and fast glycolysis, then let's say we work for 1 minute, rest for 3, and then the oxidative system, we're going to work for longer than 3 minutes. So, for somebody like a cross-country runner, they may do things like tempo runs or threshold runs where they're working at relatively higher intensities for like 20 minutes with a little rest interval, and then another 20-minute higher intensity run in between. So that would be one way to structure that. High intensity interval training. So you got these really short periods of all-out work with potentially really short rest intervals. So some of these you'll see, like the Tabata protocol is where you sprint for 20 seconds, rest for 10, sprint for 20 seconds, rest for 10. Typically they'll do somewhere between 4 and 8 work bouts for that. And so the total duration of the session is pretty short, so it's somewhere between 4 and 15 minutes depending on how you structure your work-rest ratios. But there's a couple different things you're trying to do there. Again, you're trying to work above, because you're going all out, you're trying to work well above your aerobic capacity, so you're trying to generate these big oxygen deficits and then burn more calories in recovery, so you have a really prolonged EPOC, really prolonged excess post-exercise oxygen consumption. But the other thing is, with high-intensity interval training, because you're going all out, you're training some of those larger motor units. So now you're training the type 2Xs that you're not going to recruit when you're working at lower intensities. And so that's another one of the benefits of high-intensity interval training. Combination training, which is a combination of strength training and aerobic training. The short version here is that if you do low-intensity, long-duration stuff in combination with strength training, it hurts your strength and power performance. We talked about this in the 345 class because the recruitment pattern, there are other reasons, but one of the big reasons is that the recruitment pattern is different. If you're doing all-out exercise, like if you're trying to do a vertical jump or a maximal squat or whatever, you're trying to recruit all the motor units at one time. You're trying to recruit all of them, and you're trying to recruit them all at one time, as opposed to if you're doing low-intensity, long-duration training, like jogging for 30 minutes, you're not trying to recruit all the motor units at one time. or I guess broken down. You're not trying to recruit all the motor units because you're not going to get into the type 2Xs, and you're not trying to recruit them all at one time. So there's an asynchronous firing pattern. So because of that, adding aerobic training to the workout of a sprint and power athlete can actually reduce their sprint and power production. Conversely, if we take our aerobic athletes, like our cross-country runners, cross-country skiers, long-distance cyclists, swimmers, etc., we add strength training to them, that seems to improve the economy of movement and seems to enhance their performance. Now that said, typically what you're going to do for their training is you're going to do pretty high intensity training. You're going to have them lift heavy, you're going to have them move fast. Because if you had them do a bunch of sets of like 50 and 100, well, that's what they're doing during their regular training anyway, in terms of which fibers you're using. So with those endurance athletes, you actually want to get them to lift fairly heavy to train, to recruit those larger motor units that they may not be recruiting during their typical endurance training. And that is it. Let's see how long that thing took. That seemed like forever. An hour and 20 minutes. I'm sorry it was so long, but bioenergetics is long. So we'll see you next time for Chapter 4.